The Karlsruhe Research Center is creating a new focus of attention in the Karlsruhe technology region. With the special support of the state of Baden-Württemberg, the Karlsruhe Research Center built a high-tech facility unique in southern Germany, the ANKA synchrotron light source. The concept on which ANKA is based is unique among the world's synchrotron light sources. The entire facility has been designed to solve problems of customers in analysis and micromanufacturing. Technically, ANKA is a facility generating synchrotron light, X-radiation, visible light, but also ultraviolet and infrared light, the entire electromagnetic spectrum, and all of it with very high intensity and strongly focused in space. Light is generated when high-energy electrons are deflected in a magnetic field. The electrons are deflected onto the orbit by deflection magnets. In an injector, the electrons with an energy of 70 keV, that is 70,000 electron volt, are generated in an electron gun. These electrons are accelerated to an energy of 50 MeV, that is 50 million electron volt, in a microtron, and then to 500 MeV in the booster synchrotron. Then they are directed into the storage ring proper. This process takes place every second. Each confinement in the storage ring increases the current by approximately 0.15 milliamps. Consequently, after approximately 1000 seconds, the storage ring holds 150 milliamps. After the end of the injection, the stored electrons are accelerated further from 500 MeV to 2.5 giga electron volt or billion electron volt. Quadrupoles and sextupoles are magnets focusing the electron beam. The horizontal beam size is less than 1 millimeter, while the vertical beam size is below 0.3 millimeter. In the ANKA synchrotron, electrons reach an ultimate energy of 2.5 giga electron volt. The electrons then circulate at nearly the speed of light in an annular storage tube of 110 meter circumference in a high vacuum of 10 to the minus 9th millibar. The stored electron beam up to 200 milliamps has a lifetime of at least 20 hours. Deflection of the electrons in the magnetic field gives rise to the so-called synchrotron radiation, which escapes tangentially from the storage ring. Synchrotron radiation is an electromagnetic radiation, such as sunlight or radio waves. Yet it has special characteristics which make it valuable in many applications. It covers a wide range of wavelengths from X-radiation to ultraviolet and to visible light up to the far infrared range. For most applications, especially the X-ray fraction of this radiation is of interest. The light is passed to the experimental stations in the so-called beam tubes. As required, the light is decomposed into its parts like sunlight in a prism. However, no prisms made of glass are used for this purpose, but so-called monochromators, which precisely filter one wavelength out of the spectrum. Synchrotron radiation is to be used at the Karlsruhe Research Center for micromanufacturing and for analytical purposes. Synchrotron radiation allows the interior of components and materials to be studied non-destructively. This makes the composition, structure, the chemical, electronic, magnetic and mechanical properties transparent. For instance, also glass samples can be studied whose amorphous structure cannot be determined by conventional techniques. On this basis, manufacturing processes can be controlled and optimized.